Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
John Forbes Nash 1950 paper, Equilibrium Points in N-Person Games, represents a cornerstone in the development of game theory, a field with implications spanning economics, political science, biology and computer science. This work, a concise yet profoundly influential contribution to the proceedings of the National Academy of Sciences, established the existence of what is now universally known as the Nash equilibrium in games involving multiple players. Understanding the paper's significance necessitates examining its genesis, the mathematical framework it introduced, its immediate and subsequent impact, the criticisms it faced, the individuals it influenced. The intellectual landscape preceding Nash's contribution was marked by the groundbreaking work of John von Neumann and Morgenstern in their 1944 book, Theory of Games and Economic Behavior. Von Neumann and Morgenstern laid the foundation for game theory, but their primary focus rested on zero-sum games, situations where one player's gain is exactly equivalent to another player's loss. While insightful, this framework possessed limited applicability to the vast majority of real-world scenarios, where interactions are rarely purely adversarial. These scenarios involve the potential for mutual gain or loss. Furthermore, von Neumann and Morgenstern's solution concept, while applicable to zero-sum games, did not readily generalize to non-zero-sum games with more than two players. Nash recognized the limitations of this existing framework and sought to develop a more general solution concept applicable to a wider range of strategic interactions. He aimed to provide a framework for analyzing situations where the outcome for each player depends on the actions of all other players, allowing for cooperation and competition to coexist. In Equilibrium Points in N-Person Games, Nash introduced the concept of an equilibrium point in a non-cooperative game. This equilibrium, now referred to as the Nash equilibrium, occurs when each player's strategy is the best possible response to the strategies chosen by all other players. Formally, he defined a non-cooperative game as one where players are unable to form binding agreements or coalitions. Each player independently chooses a strategy from a set of available strategies. The outcome of the game, and thus the payoff to each player, depends on the combination of strategies chosen by all players. A Nash equilibrium is then a set of strategies, one for each player, such that no player can improve their payoff by unilaterally changing their strategy, assuming that all other players maintain their strategies. Nash's crucial contribution lay in proving the existence of such an equilibrium in mixed strategies for any finite game. A mixed strategy involves a player assigning probabilities to each of their pure strategies. This contrasts with a pure strategy, where a player chooses a single action with certainty. Nash's proof relied on the Brouwer fixed-point theorem, a powerful result from topology. The Brouwer fixed-point theorem states that for any continuous function mapping a compact convex set to itself, there exists at least one point that remains unchanged by the function. Nash cleverly constructed a function that mapped strategy profiles, which are the set of strategy selections for all players in the game, to strategy profiles. He demonstrated that a fixed point of this function corresponds to a Nash equilibrium. This proof established that every finite game, regardless of the number of players or the complexity of the payoff structure, possesses at least one Nash equilibrium in mixed strategies. The immediate impact of Nash's equilibrium concept was significant. It provided a powerful tool for analyzing strategic interactions in a wide array of contexts. Economists rapidly adopted this framework to study market competition, bargaining, and auction design. Political scientists employed it to analyze voting behavior, coalition formation, and international relations. Biologists utilized it to model evolutionary dynamics, understanding how populations of organisms adapt to each other's strategies over time. The concept of Nash equilibrium offered a unifying framework for understanding strategic behavior in diverse disciplines. One compelling example of the immediate application of Nash's work lies in the analysis of oligopolies, markets dominated by a few firms. Prior to Nash's work, economists struggled to model the strategic interactions between these firms. With the Nash equilibrium, economists could now analyze how firms choose their production levels or prices, taking into account the expected actions of their competitors. For instance, the Carnot model of oligopoly, where firms compete on quantity, finds its equilibrium through the Nash equilibrium concept. Each firm chooses its output level to maximize its profit, given the output levels chosen by the other firms. Nash's work also profoundly impacted the field of bargaining theory. Prior to Nash, bargaining solutions often relied on ad hoc assumptions and lacked a solid theoretical foundation. Nash's bargaining solution, developed in his 1950 paper, The Bargaining Problem, provided a systematic approach to determining the outcome of a negotiation between two rational players. This solution is defined as the outcome that maximizes the product of the players' utilities, subject to the constraint that the outcome is Pareto optimal. The Nash bargaining solution provided a benchmark for analyzing real-world bargaining situations, influencing the design of negotiation protocols and dispute resolution mechanisms. The subsequent use and evolution of Nash's work has been even more extensive. Countless researchers have built upon his foundation, extending and refining the concept of Nash equilibrium. Refinements of Nash equilibrium have been developed to address situations where multiple equilibria exist, aiming to select the most plausible or stable equilibrium. Examples include subgame perfect equilibrium, trembling hand perfect equilibrium, and Bayesian Nash equilibrium. These refinements incorporate considerations such as credibility of threats, robustness to small mistakes, and incomplete information. The concept of evolutionary stable strategies, pioneered by John Maynard Smith and George Price, provides another significant application of Nash's equilibrium concept in evolutionary biology. An evolutionarily stable strategy is a strategy that, once adopted by a population, cannot be invaded by any rare mutant strategy. This concept closely relates to the Nash equilibrium, as an evolutionarily stable strategy must be a best response to itself. Evolutionary game theory has provided profound insights into the evolution of cooperation, altruism, and other complex social behaviors in animal populations. Despite its widespread success, Nash's equilibrium concept has faced criticisms and undergone revisions. One common critique centers on the assumption of rationality. The Nash equilibrium assumes that all players are perfectly rational and act solely to maximize their own expected payoff. In reality, human behavior is often influenced by emotions, biases, and cognitive limitations. Behavioral economists have challenged the assumption of rationality, demonstrating that individuals often deviate from the predictions of game theory in systematic and predictable ways. Another critique focuses on the existence of multiple Nash equilibria. In many games, multiple Nash equilibria exist, making it difficult to predict which equilibrium will actually be played. Game theorists have developed various equilibrium refinements to address this issue. However, these refinements often rely on additional assumptions and may not always provide a clear prediction. The problem of equilibrium selection remains a central challenge in games theory. Furthermore, the computation of Nash equilibria can be computationally challenging, particularly in large games. The computational complexity of finding Nash equilibria has been the subject of extensive research. It has been shown that finding a Nash equilibrium in a general game is a computationally hard problem, belonging to the complexity class PPAD. This has led to the development of approximation algorithms and heuristic methods for finding approximate Nash equilibria in large games. The reception of Nash's work was initially mixed. While some mathematicians and economists immediately recognized its significance, others were more skeptical. The idea of mixed strategies, where players randomize their actions, seemed counterintuitive to some. The fact that Nash's proof relied on the Brouwer fixed-point theorem, a relatively abstract mathematical result, also made it difficult for some to grasp the underlying intuition. However, as game theory gained prominence in the latter half of the 20th century, Nash's equilibrium concept became increasingly influential and widely accepted. Several individuals directly influenced the development of Nash's work. John von Neumann, whose work laid the foundation for game theory, undoubtedly played a significant role. The work of David Gale, Harold Kuhn, and Albert Tucker on linear programming and game theory at Princeton also influenced Nash's thinking. Nash himself acknowledged the influence of von Neumann and Morgenstern's theory of games and economic behavior in his Nobel Prize autobiography. Nash's work, in turn, influenced countless individuals. Prominent game theorists such as Robert Aumann, Thomas Schelling, and Reinhard Selten, all Nobel laureates, built extensively upon Nash's foundation. The work of John Harsanyi on games with incomplete information also relies heavily on the concept of Nash equilibrium. His concept of consistent beliefs, a crucial element in Bayesian Nash equilibrium, provided a framework for analyzing strategic interactions where players have private information. In conclusion, John Forbes Nash's equilibrium points in n-person games stands as a landmark achievement in game theory. His introduction of the Nash equilibrium provided a general solution concept for non-cooperative games, applicable to a wide array of strategic interactions. Despite facing criticisms and requiring refinements, the Nash equilibrium remains a central concept in game theory, influencing research in economics, political science, biology, and computer science. Its enduring legacy is a testament to the power and elegance of Nash's original insight an insight that continues to shape our understanding of strategic behavior in complex systems. It is perhaps a touch ironic that a theory so often applied to economics, a field sometimes accused of lacking real-world applicability, should itself have such a profound and practical impact on the world.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.